Hello, and thank you for joining this SaltStack webinar. We are pleased to have Mariano Alvira of Understory Weather join us today. He is an embedded systems engineer for Understory Weather. He's got about a year and a half of experience using SaltStack, and it was about a year ago that we got a proposal for a talk from Mariano to talk at our SaltConf user conference. We loved the story. We accepted it for one reason or another. Mariano wasn't able to speak at the conference, but we loved the story so much we wanted to make sure that we were able to share it with everybody. So this is the reason why we're doing the webinar, and we have Mariano on today with us. And so we appreciate him doing this. Just as a reminder, we are recording this webinar. Also, if there is any Q&A, any questions, please enter them into the chat function and the Q&A function within WebEx, and we will get to those questions at the end of the webinar. But with that, I'll turn the time over to Mariano.
Great. Thanks, Rhett. And thanks, everyone, for joining the webinar. My name is Mariano Alvira. I'm the Embedded Systems Engineer for Understory Weather. I work on the hardware and the software for our network of advanced weather stations. This is a tornado track that went through our neighborhood in Kansas. You can see it's not very wide, maybe 4 or 5 houses. And you can also see that's rather indiscriminate. The track where the tornado went through is pretty much completely destroyed, but right next to some of these destroyed houses, there are houses that are fully intact. And this is what we mean when we're talking about hyperlocal weather. Unfortunately, we don't get a lot of good local information about a storm until well after the fact. And that's because our main instruments, satellite and radar, they look up into the upper atmosphere and don't tell us much about what's happening at ground level. At Understory, we're trying to solve this problem by watching what's happening near the ground during a severe weather event. And that way, we can better tell exactly which areas are affected by the severe storm. So to do that, we've created the ARTI, which is our dedicated field scientist. The ARTI is constantly on and monitoring its sensors and uploading the data to our cloud servers, where we process it into further data products. This is a picture of the inside of the ARTI. At the bottom, we have an ambient air chamber, which measures temperature, pressure, and humidity. Above that is a housing for all the electronics. We have an embedded Linux machine that's connected to a 3G cell phone network. On top of that, we have our impact target, and that's connected to a 3D force sensor. So this measures forces from the wind as well as impacts from rain and hail. What we do is we sample that force data quite fast. It's above 3 kilohertz, and it's actually 16-bit values on 4 channels. So this ends up being quite a bit of raw data. That's about 2 gigabytes an hour. And what we're seeing here is an example of this data when hail impact occurs. Now, we could send that raw data up to the cloud and process it there. And sometimes we do that in order for diagnostics or to develop a new algorithm. But we don't like to do it very often because it's very bad for our data plan. So instead, we process that data in real time on the station using DSP techniques to reduce the data down to a smaller feature set. We can classify the impacts and determine their characteristics, such as how big was it, what direction did it come from, etc. We package that data up and send it with the rest of the sensors every second. This is a picture of the computing system that we use to do this. We use a Beagle Bone Black, which has similar computing power to sort of a 2000, 2001 era PC. It's a 1 gigahertz machine with 512 megs of RAM. It's running Debian, which we put on a 16 gigabyte SD card. We have a USB 3G modem to connect to the internet. And underneath that, we have an ARM microcontroller, which handles the real-time operations, like doing the DSP on the force sensors and interfacing to the rest of the sensors and electronics. So after we've built these stations, we deploy them up on cell towers. We put them up on roofs. And eventually we can build out a metropolitan area. So this is a map of Kansas City. We have about 30 or so stations in fairly remote locations. The cell phone towers and the roofs, they're all very difficult to get to. So what happens when you've deployed 30, 40, maybe 100 of these stations that are Linux machines out in the field all across the nation? We run into a DevOps problem. This ends up being very similar to managing a live cloud infrastructure and having to roll out new features and bug fixes on the fly. We deal with a lot of the same challenges that a traditional sort of DevOps team has to deal with. For us, the only real difference is that it's much harder for us to spin up or tear down servers, and that our servers are actually weather stations. So we ended up using Salt to sort of tackle this problem, and it's helped us out in several different ways, and I'm going to go through those details about how we use Salt and to address these challenges. So let's start at the beginning. So we have this hardware, but we have no software for it yet. What are our version 1 requirements for the thing we need to ship? Ideally, we would include everything, but realistically, we just can't. Our deployments are under severe time pressure because of storm season. We have to ship against a hard deadline that's sort of set by the deployment schedule. And there's also a little bit of lead time for when a station is sealed up on the production floor to when it's actually installed. So we have to get some version of the software ready well before we ship out into the field for production purposes. So that means that our version 1.0 software is really minimum requirements. It can only contain the things that are absolutely necessary, and then from there, we'll bootstrap all of the other functions that we need. So what's this list? Well, first thing the system needs to do is it needs to boot. And then the next thing is it needs to connect to the internet. Both pretty straightforward things that have to happen. And then the last step, we run Salt, because Salt is what we're going to use to administer and bootstrap everything once we get going. Of these challenges, booting is obnoxiously complicated, connecting to the internet is painfully difficult, but running Salt, pretty easy. So let's start with that one and go through how we run Salt and how we start to use it. Okay, so running Salt on an embedded system like ours, it has some considerations. One requirement that's not obvious at first is during the manufacturing process, we're creating an SD card with a duplicator from a master copy. And then we sort of make copies as we need it to put into new stations. So this means that the SD card has to be somewhat fungible. That means it can't matter which SD card ends up in which piece of hardware. So in practice, this means that we have to personalize each station every time it boots up to establish its identity, because we can swap the SD cards around at will, basically. So the way this works is systemd runs an each boot script. It happens every time it boots up. And what we do is we read out the MAC address from the hardware, and we use that to populate the Salt ID. So we just fill in minion.d id.conf with rd-the MAC address. And then we restart the Salt minion. So that means that no matter which SD card it has, the Salt ID is tied to the MAC address. It always comes up that way. Next thing we do is we wait for networking to come up, and then we run an after network script. So this really just does two things. The first thing that it does is it gives us a happy feeling by sending out a hello email. It's sort of just the stations announce themselves. Hey, I've come online. They include some diagnostic info like the IP address, what version of the software we have. Since it's email, pretty much everybody can get it in a variety of ways. I have it tied to a funny ringtone on my phone, so I know instantly when their stations are doing something crazy. That's not a Salt thing, but if you're working on an embedded system that can send emails, I highly recommend doing this hello email. It's been really useful. The second thing that we do is we actually trigger a Salt call from the station to enforce the login credentials for that station. So we have a custom pillar set up, and that's where we can populate in any station-specific stuff, like the logins or calibration. And so that has to get reinforced every time the system boots as well. And then after that, all of our setup is done. We launch our main application daemon, and that is called RDPy, and it just sits there running the station through its normal operations. So if you have, now we have Salt up and running. Most of our formulas are what you would typically see for sort of basic config management of a Linux machine. So on the left, you can see what we have for our top file, the top SLS. We just match everything that's an RD and apply system.rd to it. And then on the right, we have a system directory, an RD directory, and then the init.sls, which is everything that's going to get applied to things that are RDs. And this demonstrates one of my more favorite things about Salt is that it's your SLS files can be written in a very clear and organized way. So it's very easy to factor things out into sensible units that are easy to manage. So I can skim this file here and say, oh, okay, this is where packages are installed. This is where Boto, we set up its credentials. That's a Python library to interface with Amazon. And we do all the other things that you need to get a Linux machine up and running. You set up log rotate, log watch, NTP, SSH, watchdog timer, which is an absolute must for embedded systems because it's really hard to send somebody out there to go reboot them. I'm not going to go into a lot of these in detail because they're more or less exactly what you'd see on a regular server that's been administered with Salt. And you can go online, you can check out how to do all of that. It's pretty straightforward. I am going to go into this sort of understory SLS in detail so you can see sort of the heart of how we handle upgrades in our application code and some of the considerations there. So this is our understory SLS, and there's three parts to it. So our application code is stored in a Git repository on GitHub. At the top of the SLS, we check it out and install it. In the middle here, we are setting up a service in systemd to be used. And then at the end, we are telling that service to run and restart. So releases are tagged with a version number. And we set that here in this line of the SLS. To upgrade, we bump that line, and then we run a high state or a similar command from the master node to roll out the changes to the station. Now, when we do this change, we need the service to restart properly. So service management is something that can be a little tricky to set up correctly in Salt. So when you're writing an SLS file, what you're doing is describing the state of the system, what configuration you want to achieve. The steps to get from the current configuration of the server to the state that you're describing are implicitly defined. And the details of that transition are internal to Salt and the modules that you're calling. So this means that there isn't an explicit ordering in the operations in the SLS. I've listed them here. Check out the code, install the service, and then run the service. But you have to explain to Salt the dependencies in order for the ordering to get run properly. So let's take a look at that for the installing the systemd service first. We install the file rd.service in the right place, and we use a call to file manage, which is pretty straightforward. But then what we need to do is we need to run systemctl daemon reload in order to tell systemd, hey, there's a new service for you to use. And for that, we use the cmd wait command, and we set that up to watch the file. So what this will do is whenever that file changes, it'll run systemctl daemon reload. So that's sort of an isolated example of how you sort of set these dependencies up. And once you wrap your head around it, it's really not as clunky as it might look at first take. So then we have to do a similar thing to actually restart the service. So these commands here enforce that the service is running, and enable sets it to happen on boot. But then we have this requirement line, which sort of sets up the ordering that has to happen. And there's three things that have to happen first. We need the service to be installed, and we also need the application code. And then finally, systemd has to have done its daemon reload in order to have known about it. So these three requirements here will make sure that all of those other things happen first. And then finally, we set up a watch trigger. So if the Git ever changes, during an upgrade, then that'll trigger the service to restart. So that was sort of the core of how we do our upgrades and manage our application code. We also use Salt quite a bit to administer our deployments. One of the features that we like quite a bit is the node groups. So what we do is we take Kansas City, for example, and we break it into three groups, KC1, 2, and 3. The first group, KC1, just has two stations that are sort of near the middle of the city and close to other stations. That way, when we want to do an upgrade for the first time, we can just load it out on KC1, make sure it's working properly before we deploy to the rest of the stations. That way, if we actually broke something on accident, then it had minimal impact sort of to the overall system. Node groups also, so this is an example here, the command that would do that, -n KC1, and then we can just run, reinforce the understory SLS from before. That'll do the upgrade to only those two stations, and we can sort of see how it goes. You can also use these node groups to sort of ask, is Kansas City even still online? So this command here will test ping. It'll ping all of our stations in Kansas City, and we can immediately see which ones are coming back to us, and hopefully it's all of them. So that's kind of an example of how we use Salt to sort of gain situational awareness. One of the things to remember is that these systems, we don't have a user interface for them. We can't get a console once the station's all buttoned up and sealed. Salt becomes our main downstream interface to it. So, a command that we use all the time is we ask, hey, what's the IP address of this thing? So something like this will list all of our IP addresses for Kansas City, and how do we log into this station? So this gives us access to the login credentials for each station. What version of the code is running? These stations will get built, buttoned up, and then sit on the shelf for a month or two before they're actually shipped out. They don't have power necessarily while they're doing that. So they might be 3, 4, 5 versions behind once they actually get installed. So we just have Salt run a git describe to tell us, hey, what version things are running. And this is sort of a primary way that we figure out the health of our network and what's even going on. So we actually automatically do some of these checks and cache them in a database, so that, that's how we populate our list of IP addresses and such. Okay, so I mentioned that networking is complicated and that we use Salt to sort of help fix that problem. So what's going on there? So our USB stick, when you plug it in, it comes up as USB storage. And then what happens is this program called USB mode switch runs with the string 0:0, and that causes magic bytes to get sent to the USB dongle, which will then re-enumerate as USB serial and open up 4 serial devices. I don't know why they do it this way. It's just apparently what has to happen. So once all of that has happened, we run WV dial on one of those UARTs, which gives us a PPP connection to the internet. So, okay, complicated. What's the problem? Well, this part here is bugged in systemd with Debian. At least it was when we were trying to deploy this out for our first storm season. So the problem is that 0:0 gets handed around several times and escaped and unescaped, and basically with systemd it was getting passed to something that wanted colons or didn't want colons. I don't remember. We'll have to look at the patch. So normally, you'd track down the bug and try to get a patch upstream, but we just didn't have time for that. So we patched it. And here's the fix. There's some script somewhere that, the colon got escaped, but we didn't want it escaped, so we'll just unescape it again and then pass it to the thing that needs it. And normally, I'd get a lot of heartburn about doing such a change in a deployment system, but with Salt, it's actually really nicely documented and very easy to apply. So we have the file here, fixsystemd/the patch. We know exactly where it is and what we're doing to it. And then we have an MD5 sum to make sure that the patch was actually applied correctly. It's great. So now it works, and we have network. But you might be asking yourself, well, wait a minute. So if you didn't have network, then how are you even using Salt in the first place? So this actually ties into how we use Salt to fix sort of the booting problem and how painfully difficult and obnoxiously complicated booting is. So let's talk about sort of first how you typically would make those initial SD cards for an embedded system. So what you do is you take your SD card and you put it in a laptop, okay? And then there's a pile of shell scripts. Maybe you wrote some of them, somebody else wrote a bunch of them. In this case, there's a bunch of shell scripts that the BeagleBone guys have. All right, so that makes you kind of sad, first of all. But now, okay, so you need to make some updates, change some stuff around, add some more piles of shell scripts. And now, you're very, very sad. Laptop's on fire, and it's terrible. So how can we use Salt to make this better? Here's the plan. The idea is that you boil those shell scripts down to the bare minimum that you need. So in this case, you make the partitions that you want, you multi-strap Debian. That's a little painful and complicated because this is a cross-arch thing. We're making an SD card for an ARM system with our laptop, which is an Intel or AMD-based thing. But some smart guys have QEMU ARM static, which does the emulation all for you seamlessly. So you can actually get the SD card pretty much all set up how it needs to be with a few easy steps. Then what we'll do is clone our Salt formulas for how we want the system to be, and then we'll do a local masterless call to provision the SD card to the high state. So this is the goal. We do that setup script there to get us to the point where we can just hand everything off to Salt. And for updates, this is great because we're using the same system, the same code, the same formulas for everything. The stuff that we're using to deploy out in the field and provision the SD card, they're all the same sort of formulas. As we get unification, it's a huge win. But now in practice, it's still this step here. It breaks, and so the Debian config is kind of a moving target. This one script, there's still a bit of maintenance that we have to do, but fortunately, we don't actually have to make a raw SD card from scratch very frequently, because what we typically do is we take an SD card, copy it, and then we just high state that SD card to be the latest version we want, and now the new SD card is our master card that we duplicate from. So really this whole from scratch generation of the SD card, it's really just something to keep in our back pocket if for some reason we lose all of our SD cards from the other systems. That's pretty much it. So thanks so much. just want to point out we are hiring, and if you're interested in our story and the things that we're working on, you can go to understory.appliedtojob.com, and happy to weigh in on any questions. And I think we also have some of the Understory team watching too, so if there's anything I can't answer, we might be able to get them to chime in as well.
Very good, Mariano. Thank you for that. As you know, just as a reminder, if anybody has any questions, please enter them into the QA function in WebEx, and we'll be happy to address them. Either questions for Mariano and the Understory Weather team, or for SaltStack. We've got people on the webinar who can help answer those. One question for you, Mariano. Can you explain, kind of to what end? What is the business behind the technology? Why are you guys collecting this weather data, and what do you do with it?
Sure. I'll tell you what I know, and then maybe one of my team members, if I don't hit the high points, that can weigh in. But the basic idea is severe. There are a lot of industries that are keyed to severe weather or impacted by it. A hailstorm coming through a metropolitan area could do millions of dollars of damage. Since we don't have good data as to what's actually happening, what was damaged and what wasn't damaged, there's an economic opportunity there because, for instance, we're working with insurance companies, and how that plays out, there's value there that we can offer by having better data.
Very interesting. Okay. So a bit of a big data angle in addition to kind of this embedded systems and Internet of Things type scenario. We did have a question come in from one of the webinar attendees asking about how much bandwidth overhead SALT adds to your to the system setup, or to the scenario that you've outlined. Right.
That's a good question. We profiled our bandwidth usage, and there was sort of an other category that was maybe 10%, 15% of our usage, and we didn't break into that anymore. But SALT is somewhere in there. So one thing to keep in mind is that we only use SALT to do sort of downstream requests. So compared to the normal operation of the station, normally it's collecting data and uploading it. So there's actually way more overhead in sort of how we're packaging the data and uploading it compared to whatever SALT is contributing. So so far we haven't had any problems with SALT and sort of data overhead. We do from time to time run into sort of this latency issue because these 3G modems, they'll have ping times. I mean, ideally their ping times around 100, 200 milliseconds, but every now and then we'll get like 5-second ping times, or they'll just be off for a couple minutes and then they'll come back. So we have seen some things that seem like SALT doesn't, deal great with that type of a network condition. But for the most part, it hasn't been an issue.
Okay, and maybe somewhat of a related question that just came in, and I assume you can see these questions in the QA box there as well, but just asking about, have you encountered any issues dealing with such a large distributed system on remote networks? And then he makes a statement, normally similar tools are deployed on local networks with low latency.
Yeah.
Any thoughts on that?
I mean, you saw me fishing around for my WebEx. I have no idea where it is.
Okay. You need me to repeat the question, or?
Well, I think I got some chat window up. Anyway, so when you run a SALT command, for instance, like when we run high state, we have to set the timeout to be like 600 seconds or something like that. And that's a combination of either the network being, kind of not great, but really it's also these things just take longer to run on a BeagleBone. So I think in an embedded system, is actually the hardware consideration is a bigger question than the network connectivity, because Python and Salt, it does take some memory to run. So there's, the Beagle Bone is, I would call it on the higher end of an embedded system. 512 megs of RAM is a lot in this world. The smallest embedded Linux system is more like 8 megs, 16 megs of RAM. Those you probably can't even run Salt. You can usually run Python and it'll come up at 13 megs or so. So I think the hardware considerations is a bigger problem than the network. I mean, we haven't had too many network issues.
Okay, good. And let's see. Again, another similar question that was entered in the chat window, asking if the setup can handle connectivity that is connected just a few times a day to save data and traffic.
Yeah. I don't know enough about the Salt inner workings, and also I think Salt changed. They were using 0MQ at some point, but then they switched over to something else. So I believe that would come down to how does how is that handled at the protocol level with connections and reconnects. But I think just weighing in on it, if they're checking in on a regular schedule, maybe you have something that they check in every day for 10 minutes and they come online. If you know what that window is, Salt tries to hit the server pretty frequently, and as long as you're doing things when they're actually online, you should be good.
Okay. I believe, Matt, did you just come off mute, or did you want to chime in on that question?
No, I was going to. He covered it pretty well. 0MQ is still the default. We have two other optional transports, one called RATE, the Rapid Asynchronous Enterprise Transport, and then a new one called Tornado. Both of them handle the disconnect fairly well, and you can actually schedule check-in times, or basically run sort of a keep alive that looks in every once in a while. You have other customers who do similar things as Understory Weather, which is using small weather stations which check in just very periodically. They only come online a little bit. They have a script which sends out a ping, and then a state gets pushed. So you can configure it to handle high latency, low connection window configurations as well.
All right. Okay. Well, very good. I think we've addressed all the questions that came in from the audience, and I think we'll wrap up there. Again, Mariano, we appreciate you taking the time to prepare this presentation for us. And I think next step is we just need to get you to SaltConf 16, and this is a bit of a shameless plug for SaltConf 16, but it is scheduled for April, and so we'll talk about getting you out to do maybe an update on the work you're doing with Understory Weather at SaltConf 16 in April next year.
Thanks, Rhett. I appreciate it.
Absolutely. And thank you to everybody who attended.